So we're going to start today taking questions from that related rate set 2. Does anybody have questions from our related rates set 2? Oh, let me read through the answers first. All right, come on, Mr. Blue. Am I supposed to know if I have questions or not? If I don't know if I got it right or wrong yet. Fair, guys, fair. So starting at the top, number 5 is -4/3, or -1.3 repeating meters per minute. Number 6 is 200 pi cubic centimeters per second. I'm not sure what the decimal is, that 600 something. I stapled my stuff in the wrong order like I did that. Number 7 is -3/4 feet per second. Number 8 is 14 centimeters squared per second. And number 19 is 0.278 meters per minute. I didn't write down what the fraction was, but it was a yucky one.
5/8.
What's that?
5/8.
Yeah, it's probably about right. Okay. What do you guys want to start with? Is there any that we want to do? Hi, Anthony.
Actually, not. Never mind. For the homework.
Okay. Oh, you have a homework one. Got it. Any related rates problems you guys want to talk about or see done, or have questions or comments on? Adriana?
Can you do number 5?
5? Sure. Water is draining from a conical tank. The height of the water is decreasing at an unknown rate. The radius is decreasing at 1 meter per minute. The volume is decreasing by 8 pi cubic meters per minute. How fast is the height of the water changing when the water is 2 meters deep? And the radius is 3. All right. So I think that I edited this in the meantime. I don't think that this PDF that I just planted in here got edited though. So I'm just going to start by drawing myself a picture. And for these related rates problems, sometimes it's even helpful to like draw 2 sets of pictures that kind of show what's happening as time goes. You know, so like I have my tank stayed the same size, but the water level has decreased, right? So we're talking about radius and volume and height. So if I look at my picture here, which one of those have changed over time? All of them, right? Right? The radius is getting shorter, the height's getting smaller, the volume's getting smaller. So they're all variables, which means that each one of them is going to generate a rate variable when we differentiate. Is everybody okay? So far, so good? We're told that the radius is decreasing at 1 cubic meter per minute. The volume is decreasing by -8 pi cubic meters per minute. And we want to know how the rate the water is changing when the height is 2, the radius is 3. Feel good so far? So I know all but one of my rate variables, so I know that no elimination of variable is necessary here, right? Because I'm given everything that I need. So far, so good. Okay. So I'll write an equation that links my variables or my parameters together. So probably the volume of a cone is the equation that I want. So just differentiate both sides. The derivative of v is dv dt. 1/3 and pi are constants, so those are just kind of pulled to the front. But to do the derivative of r squared times h, I need to use a product rule. So I'd have the derivative of r squared times h, and then r squared times the derivative of h. So far, so good. Now it's time to plug everything in, now that I've taken a derivative. -1, that's 2, and that's the variable. And just a little bit of algebra from there. Quick question, why can't I plug in the h equals 2 and the r equals 3 until, or before I differentiate? Because they're not constants. Exactly right. So I can't, if I'm given a value of a variable, I can't plug that value in until after I've done the differentiation, because it's not a constant. If I plug it in before the differentiation, it just zeroes out. That ain't right. Does that feel okay? Others from this set. These going okay relatively? The second set still should have been relatively comfortable. I mean, you make some mistakes, that's fine, but as long as you had the right idea for the most part, you kind of read this and knew what to do, I think you're in a good spot. I just handed out set 3, we'll look at set 3 tomorrow. Not tomorrow, it's the Wednesday, we'll look at set 3 and take questions from that. Things will start getting harder in sets 3 and 4. Or you'll start seeing elimination of variable needing to occur. Does everybody feel okay? Is this helping? Feeling more comfortable on the related rate, just like forcing a little bit more practice and doing some feedback and just getting some more time to work through this stuff. So far, so good? Homework questions. I think Anthony said he had something. What are we looking at, Anthony?
We're at 24, 5.1.
Okay. You said 24?
Yeah.
Okay, so here it says use definition 2. Okay, well, I don't know what that is. I gotta look that up. There we go. Let's drop that in so we have that to reference as I'm doing this. Okay. Says use definition 2 to find an expression for the area under the curve y equals x cubed from 0 to 1 as a limit. Okay, so we'll just start. Well, I know the area is going to equal the limit as n goes to infinity of f of x. Well, let's write it this way. I'm going to write it this way. So far, so good. Now, I remember that delta x is b minus a over n, and xi is, if I'm using right-hand endpoints, which it doesn't indicate how it wants me to do that, so I think that'll be okay, is a plus I delta x. So in this problem, we're going from 0 to 1. So my b is 1 and my a is 0. It's okay there. And since my a is 0 and my delta x is 1 over n, I over n is my xi. So far, so good? Okay. So the limit as n goes to infinity. Now I'm going to start writing this out. So I'm going to have f of, when I is 1, I'm going to have 1 over n, and my delta x is 1 over n. Right?
I over n.
Right, but I is 1, because it's the first term of the series, right? And then we'll have f of 2 over n times 1 over n. And that's just going to kind of keep on going, right? Now we'll write the last one. Since they did it up there, we'll do the same thing. So far, so good. Okay. So I don't know what they really want any more than this. This seems fine to me. It says then the following formula for the sum of cubes of the first n integers is provided. Oh, I bet I know what they want us to do. I bet they want us to evaluate the f. I bet they want us to do that too, right? If y equals x cubed, then I have like 1 over n cubed times 1 over n, and then I'll have like 2 over n cubed times 1 over n. And then I'll have like, and I'm not going to write it, I'm just going to write 1 instead of n over n times 1 over n. So far, so good? So if I do that, actually, I am going to leave that as n over n, because I can have a common denominator now. All right, so if I do that, I'm going to have then the limit as n goes to infinity of 1 cubed times 1 over n to the 4th. And then 2 cubed, or 8, over n to the 4th. that look okay? All right. Now I see where they're heading with this. So I did that. And in part B, it says, the following formula for the sum of cubes of the first n integers is provided in Appendix E. Use it to evaluate the limit in part A. So notice here, that's exactly what we have here in the numerator, right? So let's make that substitution. Well, let's start A equals. So I'm going to have n times n plus 1 over 2 squared over n to the 4th. Oops, close my bracket. What type of limit do I have here? I have the limit of a rational function, right? Because my numerator, I can think of as like 1/4 times that, right? Because I can take the 1 over 2 squared out to the front. And this piece is a what degree polynomial? Degree 4. And this polynomial is degree 4. If I have a degree 4 over degree 4 going to infinity, its limit is leading coefficient over leading coefficient. So I have a leading coefficient of 1 times leading coefficient of 1. This leading coefficient in the numerator is, and in the denominator it's, so I'm going to have like 1/4 times 1, so just 1/4. Anthony, are you happy with what we did there? Yeah. So this first step was the hard part, right? Is working out like, where am I really trying to get to? And I wasn't totally sure until I really read what they asked us to use part B, and it's like, I just need to get this thing somewhere. So I just kept going until I saw that thing shake out, and it's like, now I'm ready to stop. Because in part B, I'm just going to substitute that sum out for the formula, and then I just have a limit to take care of. Is that, it's okay? Yeah. We don't have to do this for very long. Remember when we took derivatives using the limit? It lasted for like a section or two, and then we're like, never looking back. It's going to be kind of the same thing. Okay. So we're going to do this for a section or two, and then we're going to kick it to the curb and never look back. So just bear with me for a couple of days. Anybody else with something from homework? This is a tough one. Anthony picked a good one. Yeah, Sam?
I have a question, but it's from full-time.
Sure. Yes. What number you got there, boss?
I think 71.
Company estimates that the marginal cost in dollars per item of producing X items is 1.92 minus 0.002X. If the cost of producing one item is $562, find the cost of producing 100 items. So I'm going to just introduce into some notation. I'm going to say that the function c of x is the cost of producing x items. So the derivative of c then that's going to be my marginal cost, because that's like dollars per item, right?
So that's the cost for a specific unit, right? Derivative?
Well, it's going to be a function that gives you the cost, because the cost is going to change depending on how many units you're making, right?
So X would be the cost of
X is the number of items you're producing.
also for the derivative.
So X is the number of items you're producing. C of X is the cost to produce 100 items. C prime of X is the cost per item when you produce 100 items. So C prime of 100 would be like the cost per item when we make 100 of these things, right? Like when if you went to buy t-shirts, right, they'll give you a price if you want to buy 10,
Yeah.
and that's going to be a worse price than if you wanted to buy 1,000, right, per t-shirt. Because if you buy it in bulk, they're going to give you a better deal. Pretty typical. So if I want the cost of producing 100 items, I want to find C of 100, right? We're told C of 1 is 520 or 562. And we know that C prime of X is 192 minus 0.002X. So now this is just like a normal general antiderivative problem where we're given a point. So we can find the specific antiderivative. So the antiderivative of 1.92 is 1.92x. The antiderivative of 0.002x is 0.002x squared over 2. And then I have a plus c. So far, so good. To solve for the c, I'm going to use that c of 1 is 562. And I reduce this fraction here, Sam.
Okay.
And I don't know, at this point I need a calculator. I'm just too lazy to work this out in my head.
Yeah, I got it. I think I was just confused with marginal cost.
Okay. And you're good from here though, right? Like this, at this point, it's just like a normal problem once we get past decoding what the problem was telling me.
Yeah.
The key observation was that the marginal cost is the first derivative of cost. That's the key observation. If you're gonna study finance or economics or something, get familiar with it. You talk about it all the time. Okay. Let's dive into 5.2. Yes, sir. Of course. So in 5.2, we're going to take what we did last time and kind of extend this out now. Okay? We'll do the same thing, continue where we left off in 5.2 and extend things out into 5.3. And then we'll start looking at things in a more efficient fashion. So in section 5.1, we talked about calculating this area under the curve by looking at the limit of the area of these infinitely many rectangles all added up, right? Okay? But we're going to give that limit a name. So this limit, as n goes to infinity, of the sum from 1 to n of f of xi star delta x. So again, this was like the width of our rectangle. This would be like our sample point in one of those n subintervals. And really it's each. And we talked last time that you could use the left-hand endpoints or the right-hand endpoints or the midpoints or just some arbitrary endpoint, possibly, or arbitrary point in each subinterval, possibly different. And it doesn't matter if you're taking infinitely many slices, right? How you choose that x in there. So that's all the star is doing, is saying that, like, yeah, some x in each of those subintervals, doesn't matter how you choose it, will be fine as long as you're taking infinitely many of them. Everybody's okay? And we're going to call this limit of the sum an integral, specifically the definite integral from a to b. So this is going to be the same thing as that area under the curve calculation. Everybody's good? So this like symbol here is just kind of like a stretched out letter S. Why do you suppose we use this stretched out letter S? What's this thing mean? No, it's the name of the letter, but what does it mean? Sum. S for sum. Kate. Sure. Okay. Okay. Now, if this gives us an answer, right, if that area has a finite value or is something we can calculate, we say that the function f is integrable over that interval. This is like the mirror term of differentiable, right? So we saw that some functions were differentiable at a point, some functions were differentiable over an interval. When we talk about integrable, we are only talking about over an interval, never integral at a point. Because does a point have an area underneath it? No, that doesn't make any sense to talk about. So when we talk about integrable, it's always over an closed interval from a to b. Is okay with that? Okay. As a little history aside, calculus was formalized by two men working like in parallel without the knowledge of what the other person was doing. Isaac Newton and Gottfried Leibniz. An Englishman was Newton and German was Leibniz. Gosh, it might not have even been Germany when he was doing it. I don't know, Germany is a fairly known country, like an 1800s country. Might have been like Bavaria or something at that time. Anyways, whatever, aside. Most of the notation we use in our calculus study is Leibniz's. Newton's did everything like graphically, like drawing tangent lines, and like it's kind of a mess to do any like hard analysis. Like theoretically it's wonderful and beautiful and works, but like from a notation standpoint it's a god-awful mess. So most of the notation that we borrow for the calculus that we study is Leibniz's notation. So this S symbol is the integral symbol, or the integral sign. So remember, this integral sign is going to work like an operation. It's like a plus sign or a minus sign or a square root symbol, right? It's an operation that we do to a function. Is okay? The function inside the integral, the one that we're integrating, is called the integrand. The a and the b are the limits of integration. That's this talking about where we're starting our area calculation and where we're ending our area calculation. And then the dx at the end is just telling us the variable that we're using to integrate over. So it's like with respect to x. Because you're gonna, much in the same way that like when we took a derivative, we did like d dx, that's telling us that we're differentiating with respect to the x variable. Because if you hang into calculus long enough, eventually you'll start doing all this stuff over multivariate situations. Now we've done that a little teeny bit with differential calculus, where you do like an implicit differentiation where you have a function in terms of x and y, right? We did that in first semester. You hang on to this long enough and you'll start be doing like all of this in multivariates, like x, y, z. Why do we do that? What kind of world do we live in? A three-dimensional world. Oh my goodness, right? Like if we're doing anything in the real world, it probably turns into multivariate calculus. Okay, does everybody feel okay with the verbiage that I'm going to use here? So integration is the process of calculating this area under the curve. And we integrate a function over an interval. All right. So that definite integral, this is just a number. Like an area is a number, right? Like it's 5 or 7 or 13 or whatever, right? Pi r or pi, 2 pi or whatever. It's just a number. So, right? So the name of the variable we use here doesn't really matter. Everything else should be the same, whether we want to call our variable x, t, r, whatever. The area under the curve is still going to be the same area. It's going to come out to be the same number. So just if I take the derivative of x squared with respect to x, it's really the same problem as if I take the derivative of t squared with respect to t, right? If I integrate f of x with respect to x, or if I integrate f of t with respect to t, I'm going to get the same area under the curve. Is everybody okay with that? All right. This sum of these rectangles, we're going to give this a name. We're going to call this the Riemann sum. This is named after another German mathematician. I think with those dates on for Bernard Riemann, those are, I think Germany is a country by then. I think it's like 18 teens that Germany becomes a country. Pretty recent, right? Is that right, fellas? What you think? Fairly close? Yeah, okay. I don't know, close enough, right? For what we're talking about. So again, this process of adding up the rectangles for the areas of these rectangles that approximate the area under the curve is called a Riemann sum. We expect as the number of rectangles increases, that approximation gets closer to what we were looking for. If we take infinitely many rectangles, that approximation is the area under the curve. And it doesn't matter what we're using to take the height, whether we use a midpoint or that, like that, or like take the, that to be our height, or this to be our height, or that to be our height, right? It doesn't matter how we're choosing the x's to use for the heights of those rectangles. If we take infinitely many of them, we get the same thing. It's good so far? Okay. So one of the things that we're going to notice is that all of a sudden, if the heights of these rectangles are tied to a function, What if my function takes on both positive and negative values? Like the function is above the x-axis and dips below the x-axis. Well, we're going to introduce the idea of having negative area. Okay? So I have the function parts that are above the curve. Those rectangles are going to make a positive area under the curve. And we have the function dip below the x-axis. The rectangles for that section have negative heights. They're going to have negative areas. So we're going to introduce the idea of negative area under the curve. Is everybody okay with that? So now all of a sudden, when you calculate these integrals, the area under the curve could be positive, could be negative, it could be 0 if the parts above the curve and the parts below the curve are equal, if the areas are equal. Like if you look at the integral of sine x from 0 to 2 pi, the same amount above is below, right? So you could have 0 as the area under the curve, that's okay. Everybody okay with this? We'll talk about how this plays into actually doing the calculation later. I'm just introducing that this is a thing that now can happen, negative area. It's okay, it's by design. Okay. So we defined what we mean by the definite integral for an integrable function, right? But not every function is going to be integrable. So let's talk about that. All of our most commonly occurring functions, the ones that we work with all the time, are going to be integrable. So if f is continuous from a to b, it's integrable. Or if it has a finite number of jump discontinuities, it's going to be integrable. So if we think about that, if I have some function like this, we have some like discontinuity here, right? Is that going to affect our area calculation? No, because what's the area under that discontinuity? How much area is that discontinuity taking away from our area under the curve? 0. What's the width of the rectangle under that single point? 0, because does a point have any dimension, any width to it? No, man. So I could have, like a bunch of those things in there. Doesn't matter. The area under the curve is the same, whether they're there or not. Where you get into trouble is if you have infinitely many, or even more precisely, uncountably many discontinuities. So your canonical example would be something like this. So this function is a piecewise function. The function's value is 0 if the x is a rational number, and it's 1 if it's not. So even if I look across the finite interval from like 0 to 1, how many rational numbers are there between 0 and 1? Infinitely many. How many irrational numbers are there? Also infinitely many. How many discontinuities am I going to have here? Infinitely many. In fact, is there any segment of this function, any subinterval from 0 to 1 over which this function is continuous? No, right? This is a really poorly behaved function here, not integrable. But it's going to be something like you're going to need something like this to come up with a non-integrable function. All the things you studied are going to be fine. Even like, yeah, we'll get to it later. It's a later question. But like, yes, everything that you've looked at, you can do. Everybody's okay? All right. So to simplify our lives, so if f is integrable over a to b, and definition 2, if we go back and look at this, says that this integral is going to be the same regardless of how we pick the heights or the x to use to calculate the height of our rectangle. Doesn't matter how we choose that. Then let's just choose this height sensibly. Specifically, let's choose these xi so that we're just using right-hand endpoints. And let's use that to do the calculation, just so it's systematic and it's the same every time. We can cut out some of the arbitrariness. If we're allowed to choose any way to find those heights, let's just use right-hand endpoints and be done with it. We could have just as easily chosen left hands or midpoints or some other rule, but like, just pick something. This is easy to deal with. Everybody's okay? So we've lost the star because we're just going to use right-hand endpoints. We're going to choose that. Is everybody okay? So we ask now to convert this limit to or write this limit as an integral, right? Convert it to integral notation. So to do that, I need to figure out what, oh boy. Okay. I need to figure out what A is. Need to figure out what B is. And then I need to figure out what f of x is. Everybody okay? So let's look down here. A and B should be easy. What are A and B going to be? 0 and pi. Okay. So let's figure out f of x now. So this part must be my f of xi, right? So what's f of x going to be? Well, it's just going to be x cubed plus x times sine x. I just drop the i's. Everybody okay? And then I just put a dx on at the end. There we go. Converted it to an integral. No big deal. You guys feel okay? Feels like I did nothing, right? I didn't do much. If this was written differently, that could be more of a challenge. And we'll look at some of those situations where it's written a little bit differently and it's a little bit more of a challenge to backtrack it out, but not today. Okay? All right. So what we don't have yet is a way to use this thing to calculate an area. Right? We're saying that's the same thing as the area. Well, how do I use that to calculate an area? I don't know yet. We'll get there. If I want an area, if I want the value of this integral, I have to go through this path right now. Okay? So let's do an example of me walking through that path to get to the area under the curve. Everybody okay? So to do that, I'm going to have to use some of these summation formulas, similar to the question that Anthony asked about earlier, where it gave us, hey, this sum of I cubes, I can use this formula. So these are like my substitution formulas, and these are like the algebra rules that I can do to manipulate my sums so that I can get to one of those substitution formulas. So if I have the sum of I, or the sum of I squared, or the sum of I cubed, these are the substitutions I can make. Or if I have the sum of a constant, and then this tells me that I can like pull constants to the front, or I can distribute my sums across addition or subtraction. And those are like the rules that I'm going to use to do my algebraic manipulation to get to one of these substitutions that I can drop in and then take the limit. Okay, let's see this in practice, okay? Says part A says evaluate the Riemann sum for f of x equals x cubed minus 6x, taking sample points to be right endpoints, and a to be 0, and b to be 3, and n to be 6. So this is my Riemann sum formula with right endpoints. Is okay? So because we're doing n equals 6, we can say this. So far so good. I remember that delta x is b minus a over n. So b was 3, a was 0, and n is 6. So that's 1/2. And ai was a plus I delta x, or 0 plus I times 1 over n, or just I over n. Oh, yes, 1/2. Thank you. So far, so good. So let's go ahead and make a substitution. Everybody feel okay? Okay. So now I'm just going to expand this out. So when I equals 1, have f of 1/2 times 1/2. When I equals 2, I'm going to have f of 2 over 2 times 1/2. When I equals 3, I'm going to have f of 3/2 times 1/2. You guys see the pattern that's happening here and how I'm doing this, or no? This is not easy to kind of see what's going on if you're not super comfortable with these summation notations. So I can do that. Is everybody okay still with where I've gotten to? And now I know what f is, right? F of x is x cubed minus 6x. So f of 1/2 would be 1/2 cubed minus 6 times 1/2. It's like that's that. And like that's that, right? And at this point, it is like, oops, approaching calculator time. And now I just grind that to my calculator. Because everything's a number. Is that okay? On what I did to get to there? You guys don't look real confident.
Is that the final answer? Or is
Well, I have this. Now to type in my calculator and press enter.
is there like a certain number of times you do that?
So it told me n is equal to 6 in the problem. So that's how I knew how many things I was gonna have to add up with 6. Which kind of stinks, right? That's a lot of them. And the function is kind of complicated. X cubed minus 6x is kind of rough for this kind of a problem. There's kind of a lot to hang on to, but that's essentially what we're doing. Is that, you see it now? Others? You okay? Because it doesn't get easier when we go to the next step here. Step B wants to calculate this integral. To do that, we're going to have to look at the limit as n goes to infinity of our Riemann sum. Where we know that this is delta x, and this is xi, let's just do it here. So delta x is 3 minus 0 over n. So 3 over n. Xi is a plus, well, let's just say 0 plus I times 3 over n. So 3i over n. Okay here. So now I'm going to plug 3i over n into my function for f of x. Everybody okay there? Now I'm going to simplify inside that summation. So 3i over n cubed six times 3i over n oops, 2i. Everybody feel okay still? So notice that there's no i's in this 3 over n. So I'm going to kind of pull this out front of the summation, because in terms of I, it's a constant. And then I'm going to distribute my sum through across the subtraction symbol. Everybody okay with what I did there? Now if I look, the 27 and n cubed are constants with respect to I, so those can pull out front of that sum. And the 18 and n are constants with respect to I, so that can pull in front of that sum. Yeah. You okay? Now I'm in business, because this I recognize here. So I can replace that sum of I cubed with that expression. And I also had a sum of I, which I can replace with that expression. So I'm going to go ahead and make that substitution now. Notice that all the i's are gone now. The only parameter left in this is n, which is what my limit is to. So let's just do a little bit of light cleanup here, and then we'll evaluate our limit. So this guy can now distribute through to both places, right? So I'm going to have a 81 n to the fourth, and then a 2 squared. And in the numerator, I'm going to have n times n plus 1 squared. Over here, I'm going to have 3 times 8, 54. And then n times n plus 1. And on the bottom, I'm going to have n times n, so n squared, times 2. Like that. And now I'm ready. What type of limit are each of these? Rational functions. What's the degree of the numerator in the first one? To the fourth, because I have an n squared squared. And the bottom? Fourth. So this limit is just going to be leading coefficient over leading coefficient, or 81 over 4. And then I have minus over here. Rational function, so I have 54 over 2. And there's my answer. Woof, Mr. Kulik. Woof. That was a lot of stuff. We spent like, I don't know, 20 plus minutes on this one problem here. The way it's gonna, I won't ask you to do this very often here in the homeworks, but this is what finding that area under the curve is going to look like until we start building in the shortcuts. And that will start happening next time. Just FYI, for next class, there will be no homework quiz on 5.2 because we haven't finished 5.2 yet. And there's still some more to talk about. You should do the related rate set 3. We will finish 5.2 and get into 5.3 next time. Okay? So it might just be like a homework quiz class behind. Also, the related rates sets I've been giving you, can you put those into OneNote? I want to check those as homework problems also. So if you guys haven't done that yet, please make sure you're putting those in there. That's it for me. Have a good day. Thank you for your patience.
I will. I've got nothing to lose. Do it. I don't want to do it. I'm not gonna do it because I already know I'm gonna get it. So I'm not doing it.
Okay, but like, if we kick out all the offsets, we get